Hello everyone. It's my pleasure to be able to introduce this paper to you a little bit. My name is Eric McCalla. I'm an associate professor at McGill University and one of the corresponding authors on this paper. The other corresponding author, Maxim, is a researcher at Umicore. And so Umicore has been working, and a lot of people around the world have been working on lithium-rich layered oxides as cathodes for lithium-ion batteries for almost 25 years now. And one thing that's very attractive of these materials is they have no cobalt. It's just nickel and manganese and then excess lithium. And they have some very strong properties for battery performance, but they also have challenges. And so this collaboration started trying to overcome some of those challenges. And the main one is that the extended cycling continues to suffer from a number of problems, and a very important one of which is transition metal dissolution. So nickel and manganese both dissolve from the cathode and get transferred over to the anode during battery use. And this is extremely detrimental in the long-term cycling. And so we utilized high-throughput methods. So this is a strength of my group at McGill. In this paper, the lead authors, Alex Abad and Nushin Zanali, made over 200 different materials, so 57 different dopants, and they were synthesized at 3 different synthesis temperatures. And what they found is a lot of the materials were single phase, which is very encouraging, so we did X-ray diffraction. And the electrochemistry, which we test in our high throughput cell. So we deposit 64 different electrodes on this printed circuit board and then assemble it into a single cell with one piece of lithium on the other side as the counter, and then cycle them doing cyclic voltammetry. So this is our usual methods in the group. And when we did this, we found some really strong performance. But it doesn't give us a lot of information about long-term cycling because we run them for about 5 to 10 cycles. So we also developed for this project a high throughput measurement technique to determine how much transition metals are dissolved. So we did a week-long high temperature hold where the cell wasn't a single piece of lithium anymore. It was 64 different punched separators and lithium assembled into one cell. And then we retrieved all of that lithium, those 64 different lithiums, dissolved them so that we could do elemental analysis. So we did ICP and determined that some dopants and some synthesis temperatures led to greatly reduced transition metal dissolution. And some of those materials also showed higher capacities than the undoped. So we were able to make better materials, and we could do it in a very accelerated manner. And we then wanted to learn what it is about these materials that makes them better. And when we tried to plot correlations, you'll see it in the paper, it's very hard to learn anything. Even parameters that we know are important, like the crystallite size, show very poor correlations. When we plot transition metal dissolution versus the crystallite size, we get a box. And we see a lot of boxes in the correlations in this paper. So we utilized machine learning. And there we were able to get a nice correlation between the predicted value and the measured value. And then we could change one input at a time to see what the machine had learned. And so when we changed just the crystallite size as the input, the predictions all shifted very systematically. So the machine knew that crystallite size was important, and it knew in what direction it moves. So we were able to learn from this trained model. And so this is part of the research in my group, which I'm very excited about. We're starting to leverage machine learning more and more with our large data sets, which we trust. And I think this is going to be a very exciting direction for the research of my group going forward. And this paper is a great example of that.